Discover, develop, deliver. The Air Force Research Laboratory leads the discovery, development, and delivery of war-fighting technologies for our air, space, and cyber forces. Our scientists, researchers, and professionals reimagine what's possible, creating tomorrow's technology today. This pursuit of innovation delivers solutions for our warfighters' urgent needs, creating innovative new capabilities for the Air Force. When others say it's impossible, we find a way. We are the Air Force Research Laboratory.
Hi, everyone. I'm Chris Vanderheide from the Air Force Research Laboratory. I actually work for the Rocket Propulsion Division out here at Edwards Air Force Base. We're under the Aerospace Systems Directorate. All that to mean is that we actually do rocket science. We do rocket motor research and do specific things for the Air Force, as in discovering how to build new, unique things, such as new fuel for airplanes, new fuel for rockets, and all kinds of things that are related. So I'm a computer engineer by trade. I have a bachelor's in electrical engineering from USC, go Trojans, and I also have a master's in electrical engineering from Cal State Fresno. And I live and I have grown up in the Antelope Valley. I've been here pretty much my whole life. I also am married, so I wanted to say hello to Mrs. Vanderheide and her class from Desert Rose School and in the Palmdale School District. And so I principally originally worked with computer networks, doing computer networking. So you guys know the internet? Well, I helped to try and build that and build parts of that. So specifically building it for the Air Force Research Laboratory and doing computational research. So basically using computers to try and figure out ways to figure out new chemistry molecules, new ways of doing things, new ways of figuring out how to make things better, more efficient. So we work on all types of rockets in Air Force Research Laboratory. We work specifically on liquid, solid, and plasma rockets. So plasma are a really unique rocket in that they only work in outer space, but we work on all the types of rockets. So if you see a rocket go up, well, we've helped research and develop that technology to make that rocket work. We've been doing that since approximately 1953 and been doing research since basically the inception of the Gemini and Apollo programs. So, why do we have rockets? Well, that's a good question, which is basically we have rockets to put things in space because it's very, very difficult to reach space without something like a rocket. I mean, we've tried airplanes to get way up into the atmosphere, but just to getting that next little step, getting out of the atmosphere, you need something that can live in space. And the only thing that can do that is a rocket. That's mainly because rockets have both the fuel and the oxygen, oxidizer as we call it, in a rocket. And so they're the ones, because both of those are on there, they can operate in what's called a vacuum. And so we in the Air Force Research Laboratory also really try and find ways to do it more efficiently, less expensive, and try and figure out ways to build rockets so that they get bigger payloads for the same amount of thrust or the same amount of fuel, and get ways of getting payloads into space. So, or put people into space. So principally, all of these rockets that you saw probably in the last couple days, putting people on the space, getting people to Mars, those are going to be rockets that we help develop and help put people into to space that way. I have another video to show of a new rocket that we're developing. It's a modular rocket that's supposed to be very cost efficient and be able to be used in different ways to be built so that we can support rockets of different levels and use the same technology to do that. So go ahead and cue up the armor video.
These test stands, located in the desert of Southern California, are where the Air Force Research Laboratory tests rocket engines and rocket propulsion technology. From the earliest days of the United States push into space, these facilities have stood on the cutting edge of launching America's rocket booster. And today, the Air Force is developing what could prove to be another revolution in rocket engine design and manufacturing. The program is called the Affordable Responsive Modular Rocket, and this is AFRL Tech.
So ARMOR stands for the Affordable Responsive Modular Rocket. ARMOR is really interesting because what it poses to do is change up how we develop liquid rocket engines. Most launch vehicles, if they're trying to put something into orbit, into space, we have the boost stage and then we have an upper stage, right? Traditionally, as of now, when we have a vehicle that has both the boost stage and upper stage, those engines are different. They're completely different. They have completely different development life cycles. They sometimes may use some common hardware between the two, but for the most part, they're different to an extreme amount, right? So what we propose with ARMOR, we can take the same hardware that we're using in the boost stage engine and actually apply it to the upper stage engine. So that reduces the development or the parallel development paths that you might need when developing new engines, and you can actually even custom tailor for both the boost stage and the upper stage, making sure that it works in both applications. ARMOR platform uses the Aerospike engine configuration because it just helps enable that modularity.
Traditional bell-shaped rocket engines are designed for efficiency at specific altitudes. The ambient air pressure at any given altitude is taken into account when designing a rocket engine bell. In an Aerospike design, the engine bell is turned inside out, with the ambient pressure acting as one side of the engine bell. This serves as an altitude compensator, yielding an engine that maintains optimum performance across all altitudes.
So that reduces the development or the parallel development paths that you might need when developing new engines or developing a new vehicle architecture, whatever it may be. We are using a lot of modern, advanced manufacturing processes and practices to make it happen, to realize it. Additive manufacturing, right now, we can print within build volumes up to about, just say, a cubic foot, right? 1 by 1 by 1 feet, right? And within that, we can potentially build and print one of these smaller engine chambers. And we can take that smaller engine chamber, put it on a lab scale bench test setup, right? And we can fully test it, and we're seeing full scale conditions, right? Because for me to actually test this, right, it requires me to set up a huge test facility, all the propellants, or the liquid oxygen, or the...
So that was the ARMOR video, or the Affordable Reusable Modular Rocket. Really it shows some of the unique things that we're trying to do in Air Force Research Laboratory, showing that we're trying to do modular rockets, trying to make them more affordable, also make them able to meet different demands of the rocket mission. We actually build rockets to fit each specific mission. So we build them for a specific thrust, as we call it, which is the push of the rocket. to meet that specific mission for the length of time the rocket needs to actually thrust or push the payload it has. And you know, the key to that is research. So to us, the key is figuring out all the little details, all the little things it takes for the technology to be used in rockets. And so we've looked at the unique things that the materials we build the rockets out of. We look at the types of fuel we use. We look at the insulation that we use, the coatings that we use. So we look at all the different aspects of rockets and how those work together, how the rockets use the fuel and how it mixes together. We do models of all these. We do computations on all of this just to try and figure out how to make rockets more efficient, how to make them better. And really, we use science. So I think you've all learned a little bit about science, about how to ask a question, basically make a theorem, and go, hey, maybe this is something that can turn into reality. And so we do that every day in the Air Force Research Laboratory. We're trying to take ideas and make them reality and develop the technology that our warfighters need to succeed in the air and space realm. And you know, we take those ideas. Basically, you've heard from a number of people about innovation, and really that is just taking a unique idea that somebody has and bring it in it to fruition, using your inspiration from that idea to push you forward. And so we want kids of all ages to look at things differently, to look at things so that we can get new ideas of how to do things and see if they can become a reality. And sometimes we fail. Sometimes the thing that we think is going to be a great thing doesn't turn out to be as great as we thought. And so you saw one of the things he mentioned in that is the linear Aerospike engine. So that was actually a technology that was developed back in the 60s, and has been tried to be used on a couple other rockets up to date, but now we're using it as the main technology in this engine so that we can develop the best and most efficient engine that we can for the Air Force. So I talked a little bit about space and about why rockets have to have both fuel and oxidizer as they operate in space. Because space is a void. There's basically nothing when you get out of the atmosphere, you get into space, and you know, there's no gravity, there's no air. And so like cars use the air in the atmosphere to work. Well, now when you get out of the atmosphere, you don't have any oxygen. So the oxygen you're breathing does not exist out in space. And so we have to take both that oxygen with us, or the oxidizer as we call it, and that fuel, so that's like the gas you put in your engine, your car, and take those out into space with us so that we can operate in space. And same thing, if you want to live in space, you're going to need oxygen and something to keep you safe. So that's why there's space capsules and all that. So so an interesting thing happened a few months ago, almost a year ago now, really. We had a new service. So the U.S. Space Force was formed. And so I want to roll the next video and show you how AFRL is going to be supporting the U.S. Space Force.
On December 20th, 2019, the United States took a giant leap into the next era of military defense. Recognizing the threat to U.S. national interests, a new force was established to protect our freedom to access and operate in space, the United States Space Force. With a mission to keep the space domain secure, stable, and accessible, the United States Space Force will protect U.S. and allied interests in space and provide new and current space capabilities. But this can't be done alone, nor will it be. Since 1917, the Air Force Research Laboratory has been leading the discovery, development, and delivery of warfighting technologies for our air, space, and cyberspace forces. Already on board, AFRL is continuing to provide the technology and resources necessary to help the United States Space Force build a comprehensive military advantage in space. With a strong commitment to innovation, AFRL ensures the United States Space Force will have the technology to keep the space domain secure, stable, and accessible for now and into the future. AFRL, carrying space research and development into the future.
So that was a quick video just to show how the Air Force Research Lab is supporting both the Air Force and now the U.S. Space Force. You know, we had, back in the 1960s, we had the race to space. And, you know, with the Gemini and Apollo missions and trying to get to the moon. And really, space is a very important area. And U.S. Space Force was formed because we really need to place the importance on accessing that arena, controlling that arena, having it be stable. I mean, there's over 300,000 objects in space right now, space junk as they call it, of about 1 inch or greater. And so having, like you saw in the video, having items fly around in space and crash in our satellites is not a good thing. And so having the ability to move out of the way of something that's going to crash into a satellite, or just to even detect that a piece of an object is coming at our satellites is an important thing. And so we have satellites that do all kinds of things, such as communication. I mean, detecting weather, detecting changes in the Earth's crust. There's a lot of things we do with satellites. And so having control of that and that arena is an important asset for the United States. The lesson that's coming up is unique to me, because being a computer engineer, I think waves are very important. Waves are very important because really waves are sound. I mean, you hear me talking and the waves are coming out of my mouth, coming to, well, it's really coming across through the TV, through to your ears, but waves can be anything. Actually, light is a wave, radio is a wave, sound is a wave, and so they are broadcast from a source. And so I don't know if you've ever dripped a drop in a thing of water and saw the waves created from that drop. That's exactly how they propagate. And so waves in a medium propagate, as they call it, or in air, propagate because the air molecules vibrate. Well, electromagnetic waves don't need that. And so radio, as we're calling that, or light, are electromagnetic waves. And that's how they actually use communications between satellites, is they use radio or light waves to communicate between satellites. You saw the little lasers shooting out of the satellites. So that's how they were communicating. Well, we use radio waves in all kinds of things. I mean, cell phone is a perfect thing. They actually use radio waves to communicate. It's kind of like, I don't know if you guys have ever heard of walkie-talkies, but walkie-talkies were an older technology that then they made digital, and now cell phones are a culmination of that technology. And really what it does is you talk, and the speaker in your, or the microphone, excuse me, in your cell phone records your voice electronically, converts it into electric waves, then transmits it over the air through radio to a tower, then through the internet to another cell phone, and then back to out of the speaker and back to sound. And so as the speaker vibrates, it creates the sound waves that you hear. And so, and same thing with cameras. Cameras convert light now into digital form, which is really cool. And then the digital form broadcasts across the internet. And we can capture that, you know, and we can send that across to anybody in the world. So, you know, I talked about propagation and conversion. So, you know, one of the things unique is about the internet. I mean, the internet communicates too. They communicate from one computer to another, and they use, again, waves. They sometimes use light or electromagnetic waves through what they call fiber optics. So if you've ever seen a fiber optic cable, that can transmit light through it through thousands and thousands of miles to get information across the United States very fast, speed of light, if you know. So I wanted to talk a little bit about waves. There's a really fun experiment. Hope you guys get to do it using waves and sound. So you guys have an enjoy day, and we'll go to a few questions.
Perfect. Well, thank you, Chris, for that. We have gotten a lot of questions from the students that are really interested in rockets. So here is the first question. How many parts does a rocket have?
Oh, gosh, a very good question. So rockets have a lot of parts. So it depends on the type of rocket. So like I said, there's liquid rocket engines and solid rocket engines. So solid rocket engines are actually much simpler. So they make the fuel and the oxidizer, they mix them together and make a solid mix. So it's kind of like the rubber on your pencil. So they mix it together and mix it with what they call a polymer, which is a rubber, and pour it in there. And so really for the solid rocket, you have the case, we have the thing that's called the insulation, and then you have the solid rocket fuel, and then the nozzle and the parts of the nozzle, so, and the igniter. That's really all the parts of a solid rocket motor. But then a solid rocket engine has much more parts. It has, oh my gosh, probably anywhere from 10 to 20 to 30 parts, maybe a couple hundred parts in the rocket. As you saw in the modular rocket, that had probably a few hundred parts because it had the thrust chamber, it had the igniter, it had the pre-burner, so it has all these parts I'm naming are different parts of a liquid rocket engine. And that's kind of like the engine in your car. And you've seen a car engine, well, that has lots of parts too. And so it depends on the type of rocket, I guess, is the answer to that question.
Awesome. Okay, another question is, how much thrust is in a rocket?
Well, that depends again. So it depends on if it's a little rocket, because we can have rockets that work in space with just what they call pico amounts of thrust, and really we have plasma rockets that only put out like thrust that's about the weight of a piece of paper.
Oh, wow.
And then we have the big rockets that put people into space, and they go up to hundreds of thousands of pounds of thrust. So the Saturn V rocket, which actually put people into space for the Apollo mission, so that had each Saturn V engine had 1.3 million pounds of thrust. And so that's about the same power as 300 locomotives, which is still hard to imagine. And you got to imagine that that's just one engine. There's actually 5 of those, so over 6 million pounds of thrust on that rocket to put somebody, basically a bus-size capsule and 3 men into space. And so it just depends on the mission you're trying to do and the thing you're trying to do. So it can be, we can do thrusts of millions and millions of pounds, or we can do thrusts of tiny, tiny amounts. It all depends on what we're trying to do with it.
Okay, so it looks like we have time for one more question. And the question is, do you like your job? And what is the best part about your job?
Oh my gosh. So I love my job because I get to talk, right now I work STEM, and so I get to talk with kids all the time. And that's probably the most fun part of my job, is to see kids get excited about engineering and science, because we need kids to become engineers and scientists. We need people to invent new airplanes. We need people to invent new rockets and new technology. And so we really need kids to come and get excited about the things we do. This is like we're doing this today. I just want kids to be excited about things. I mean, I want kids to come into computers and science and the science of computers to figure out new ways of working computers so that we can figure out how to make computers smaller. I think they're pretty small already, but I mean, even smaller computers would be even cooler. And so there's people trying to figure that out right now, and we want kids to follow us in that and develop new computers. I mean, I would love to see a computer that, you know, you could like pop up the size of your watch or is on your fingernail, and you can then talk to somebody, have a hologram pop out of your fingernail. That would be like cool. So.
Okay, and it looks like we actually have one more time, or time for one
awesome.
more question. And this was a pretty popular question. How long does it take to build a space vehicle or rocket? Good
question. Well, it typically went, so back in the F1 days, it took almost a year to put the rocket engine for the F1 engine together for the Saturn V rocket. Now, they have sped that up, and we are trying really to get rockets put together in less than 6 months. Really, if we could do it in 3 months or even 1 month, we would do that. And the other thing too is we're trying to do it so they're reusable. So we can take that rocket, launch it into space, bring it back, refurbish it quickly, and be able to use it again within a month or two. And so that's part of being efficient, and so that we don't waste that rocket engine, use it once and throw it away. We can use it multiple times, hundreds of times, possibly even thousands of times, depending on the life cycle of that engine.
That's pretty quick for a rocket.
Yeah, it is very quick.
So thank you once again, Chris, for speaking to the students and showing them what you do with your career. And next we'll head over to the NASA professionals, and they will be going into your next lesson.
Thanks for having me.
Good morning. Welcome. Thank you for joining us at the Aerospace Valley Air Show. We would like to thank Edwards Air Force Base 412 Test Wing for this amazing opportunity to live stream and connect with you. Bienvenidos. My name is Monica Uribe, and I'm the NASA's APDCS Educator Specialist for Armstrong Flight Research Center. Let's share the screen. So in this picture, you can see me, and behind me is Armstrong Flight Research Center. That's the Supersonic X-1. And on the side is Sara Torres. She is a specialist at Ames. NASA has a lot of centers all over the country. It's not just the Kennedy Space Center where we launch the amazing rockets, or Johnson Space Center where we train the astronauts. We are located in California, and if you can see AFRC, that's where I'm located at. That's the Armstrong Flight Research Center. It's South California, and we are inside the Edwards Air Force Base. And North California, you can see the ARC, that's Ames Research Center, and Sara Torres is my colleague, is working there. Today we will explore, because in NASA we do explore. What is sound? Sound is a vibration that travels as a wave. Let's try it out. Place your fingers on your throat and talk and say, that is sound. You can feel it because your fingers are connected right now to your throat, but sometimes we cannot feel it. But sound is something that we produce. How sound travels? Does sound travel from one place to another? I think so. We will explore. How do we measure sound? Ooh, that's a good question. And we're gonna share with you the NASA activity. This activity belongs to one of the next gen STEM teams from NASA. One is Artemis, or Explore Moon to Mars. The other one is Small Steps to Giant Leaps, who focus in aeronautics. And today we're gonna focus on Sound on the String, which is one from the Commercial Crew Program. How sound travels. This is the activity that we will explore today. And what do you have to do with this activity? We're gonna explain how sound travels, and we're gonna demonstrate how the transmission of sound waves is affected by different materials. We will use simple materials. Remember, if you don't have any of the materials we suggest in this activity, you can just use whatever is around your house. But what is Commercial Crew Program? Let's watch a video.
NASA's Commercial Crew Program is ready for launch. Did you know the last time we launched astronauts from America was in 2011?
NASA is working with companies Boeing and SpaceX to take astronauts to the International Space Station from America once again. Let's look at how this will happen.
Look at the spacecraft on top of the rocket. This is where humans will be sitting. The astronauts will be buckled into a spacecraft stacked on top of the rocket as it is launched into space. The rocket holds all of the fuel needed to get to space.
It takes a lot of energy to lift the rocket off the ground, with gravity constantly pulling it down, which is why most of the rocket is filled with fuel. During the rocket's climb to space, it will increase in speed, which means its energy will also increase. Once the rocket has made it past Earth's atmosphere, the engine will finally cut off. The rocket and the spacecraft will separate, and the astronauts will make their way toward the station, where they will be working on science experiments and engineering projects.
What do you think will happen when the spacecraft travels back to Earth?
Boeing has made the Starliner CST-100 to keep astronauts safe as they travel to and from the station. It's designed to touch down safely on land in the western United States. The Starliner has parachutes it will use as it prepares for landing, but will also have large airbags expanding under the spacecraft to cushion the landing for the astronauts before stopping completely.
SpaceX's Crew Dragon was also created to send astronauts to and from the space station. As the spacecraft comes back to Earth, the outside will experience temperatures over 3,000 degrees Fahrenheit. The Crew Dragon has been designed to keep the astronauts inside comfortable during the ride home to Earth. Once they're back in the atmosphere, the spacecraft will release 4 main parachutes to slow down the speed and energy of the vehicle before it splashes down in the Atlantic Ocean or Gulf of Mexico. These spacecraft are exciting sneak peeks at the future of space travel.
And NASA's Commercial Crew Program.
Want to know more about space travel? Check out this website for more information.
So, I mentioned that Commercial Crew Program is one of the three next gen STEM science teams from NASA. But what is next gen STEM? Well, NASA's Office of STEM Engagement develops STEM products and opportunities that provide a platform for students to contribute to NASA's endeavors in exploration and discovery, driving opportunities that enhance STEM. That means science, technology, engineering, and mathematics literacy, and help build a diverse next generation STEM workforce. But let's keep going with rockets and sound. How is a rocket launch like a rock concert? If you have ever seen a rocket launch in person, then you know the roar from the engines during launch can be heard and felt miles and miles away. How does tuning a guitar related to rocket science? Like a guitar, every sound and vibration passes through the body of a rocket. The difference between them is the musicians wants to sustain these vibrations and amplify the sound, while the engineer or the scientists who work to reduce the noise in the rockets. Engineers can verify the structural integrity of the rocket and measure its stability and perform. What is sound? Sound is one of the many forms of energy. Sound is produced by vibrating objects and travels from one place to another throughout vibration matter. But what is matter? Matter is anything that has weight and takes up space as a solid, liquid, or gas. Look at this picture. We are showing you the different states of this matter. NASA studies whether matter acts differently in space than it does on Earth. Gases, liquids, and solids are these states of matter. The speed at which sound travels from one place to another depends upon the medium. That means if it's a solid or liquid or gas, and how closely packed the molecules are in the matter. A medium is a substance that allows sound waves to travel throughout it. Sound waves travel the slowest throughout gases, faster throughout liquids, and fastest throughout solids. Ooh, interesting. The matter sound travels throughout is a color medium. We said it. Sound travels in the form of invisible waves called compressions or compressional waves. Remember, waves. Unlike water, waves that move up and down, sound waves move toward and away from the source. We have to have a source in order for we to produce a sound. And then the sound travels in waves. Pitch and loudness are two important properties of sound, waves that affect human hearing. The pitch of a sound, how high or low the sound is perceived to be, is determined by the speed of the vibration. How high or low. How fast the molecules in the medium are compressed and then spread out. Pitch is also referred to as the frequency of the sound wave. Frequency is measured in units called hertz or Hz. 1 hertz is equals to 1 vibration of wave per second. Healthy human ears can hear sounds in the frequency range for 20 to 20,000 hertz. But How is that? And we have waves. As we mentioned, sound waves is the name given to the pattern a sound creates and can be seen on a waveform monitor. A single tone, such as the produced by a tuning fork, creates a very uniform wave. If we can appreciate it here on the graph to the right. While human speech, with all the inflections and changes in tones, up and downs, quiet and loud, cause a much more erratic looking one graphic. Since sound waves spread out as they travel away from the source, the sound intensity decreases over the time. So this is the farther you are from the object who is producing the sound, the less than you can hear it. The tuning keys on a guitar adjust the tension on each string and thus change the pitch or frequency of vibration. The guitar string vibrates more slowly when it is longer, resulting in a lower frequency or lower pitch. Imagine a slinky. We can see how the sound travels in the form of invisible waves called compression. Unlike water, waves that move up and down. Let's watch a video about how sound travels.
NASA's newest experimental airplane, the X-59 Quest, is designed with quiet supersonic technology and is intended to help open a new era in faster-than-sound air travel over land. Now under construction by Lockheed Martin Aeronautics Company, the X-59 is designed so that when flying supersonic or faster than the speed of sound, people on the ground will hear nothing more than a sonic thump, if anything at all. You must first know what sound is and how it travels. Every sound we hear is produced by vibrations. These vibrations create sound waves, which can move in all directions through materials like solids, liquids, and gases. A sound wave is a compression or longitudinal wave, where the disturbance moves in the same direction as the wave. Frequency is the rate of vibration or the number of compressions or refractions that pass a point in a fixed amount of time. In a sound wave, increasing the rate of vibration increases the frequency, also increasing the pitch. The amplitude of the wave is the maximum height of the wave and directly determines the volume or loudness of sound. An increase in amplitude corresponds to an increase in volume. As sound waves travel, they lose energy, which is why you can only hear sounds up to a given distance.
So knowing about how sound travels is very important to NASA scientists and engineers as we design supersonic aircraft. Perceived levels of noise of the sound waves reaching the ground can be 105 decibels or higher. In other words, a typical aircraft traveling at supersonic speeds is about as loud as a rock concert. The X-59, however, is designed to be much quieter. We expect the X-59 to reach perceived levels around 75 decibels in supersonic flight, which is a little bit quieter than closing a car door. Generally, commercial aircraft fly at altitudes of 36,000 to 41,000 feet. The X-59 will travel at approximately 55,000 feet above sea level. At this altitude, the X-59 will be flying at a height roughly 44 times higher than the Empire State Building and nearly twice the height of Mount Everest.
So, is there a difference in how I can hear and my dogs can hear? What do you think? I think yes. We measure the frequency of sound waves or pitch in a unit called hertz. It is named for Heinrich Rudolf Hertz, the first person to provide conclusive proof of the existence of electromagnetic waves. Humans have a normal range of hearing between 20 or 20,000 hertz, which is different from many other animals that you can see in this slide. The loudness of sound is determined by the height of the sound waves. Scientists call this the intensity or amplitude of the waves. Adding more energy to the object, creating the sound waves the wave higher, producing a louder sound. Loudness of sound is most commonly measured in decibels or dB. If you can appreciate in this graph, look at the gunshot between 130 or 135 decibels. And look at the firework, 115. Look at a car door slam outside the car, about 90 decibels. How can we hear? The human ear is an amazing instrument for capturing sound, and it has to do with vibration. The visible parts of the ears is shaped to catch sound waves as they travel through good air. When the vibrating air molecules hit the eardrum, it starts to vibrate, and then we can have sound. Let's explore. We mentioned already that this activity belongs to one of the next gen STEM themes, which is commercial crew program. Let's see why we need commercial crew program. What is talking about?
The International Space Station, one of the nation's great assets for research and discovery, is in low Earth orbit. And the International Space Station, providing transportation to ISS for research and discovery, that first step in low Earth as a gateway to space. And the commercial crew program will be providing transportation to ISS to support that first step as a gateway to space.
Capabilities and the research that protect our Earth orbit for these deep space exploration to develop the systems that we'll need and the
International
capabilities
Space
that we'll
Station
need to
is
protect
our
our
orbiting
crews for these
laboratory,
deep space
and it allows us
exploration
to do
missions.
research on life and physical sciences, Space Station and really understand the impact of and it allows us to do research on life and physical sciences, understand how organisms and really understand the impact of living without gravity. Think about understand how humans and other organisms might survive on other planets. Then we'll be able to think about how humans and other organisms might survive on other planets.
Right now, one of the biggest constraints we have on station is the available hours for astronauts dedicated strictly to work. Right now, one of the biggest constraints we have on station is the available hours for astronauts to be dedicated strictly towards research.
To the space station. That's why we're so excited by the commercial science program, because it'll be
A lot of
bringing
the
additional
technology we develop on
astronauts.
space station has come back here.
So commercial crew program is a program to take astronauts from and to the International Space Station to do more research. So this is a comparison of these are two pictures from Boeing, which is a SpaceX and a SpaceX with Dragon. Boeing with the Starline and a SpaceX with Dragon. If you remember, these astronauts were the first SpaceX Demo 2 mission, Douglas Hurley and Robert Behnken. They were the first astronauts, commercial crew program astronauts who traveled to the International Space Station to do research. Now we are getting ready for this coming 31st, yes, October 31st. And they're gonna have the Crew 1, SpaceX Crew 1. The names of the astronauts. From left to right, Shannon Walker, Victor Glover, Mike Hoppings, and astronaut Soichi Noguchi. He is from the Japanese Aerospace Exploration Agency. The SpaceX Falcon 9 rocket that will launch NASA's Space Crew 1 mission for the agency commercial crew program is ready. NASA and SpaceX are preparing for the company's first operational flight of the Crew Dragon spacecraft and Falcon 9 rocket after certification. So we are ready to go. Now, let's explore the activity. My hypothesis, or I think, The plastic cups are gonna be working better to do the experiment and the activity that we're gonna be doing. So we're gonna explore some questions, but this is the objective. Materials, several kinds of strings, several measures, different types of cups, scissors, tape, paper clips, and something pointed to make a hole on the cup. Remember, if you don't have any of these materials, you can find the closest one that you have near to you at home. Let's watch a video. Use a paper clip of a washer to secure your string inside the cup. Remember to follow the steps and ask the help of your parents or an adult. We start with a foam cup because that was easier. Don't forget to take your notes. Gather that data. Now, these are some other models. We use a plastic cup, and we made one of the carton stuff. Try it out, and don't forget to keep getting data. One more of the activities that we can share with you is senses of sound. These belong to the small steps to giant leaps. In this activity, you're gonna be able to see, hear, and feel the sound. This activity is really interesting and it's really nice. Remember, if you don't have these kind of cups, just substitute it for whatever you have near to you. Discussion questions. Did the size of the cup affect the loudness or clarity of your partner's voice? I think so. Yes, for me, it's a yes. Which size will you select? I think the biggest one. What is sound? How does sound get from one place to another? How do we make sound? How do we hear sound? Additional resources. Remember, sound travels and we can hear it. We can feel it and we can see it. If you have any questions, ask your teacher or your parents. Thank you.